Our keynote today is by Vitaly Shmatikov from Cornell Tech. He's a faculty member there who really doesn't need any introduction, and he is also far too modest to provide us with a lengthy bio. So let me just say that he used to work in security and privacy, and you might know him from breaking the anonymity of the Netflix price dataset, for example. He recently became interested in federated learning, and of course he immediately went to work trying to break FL as well. But fortunately for us, he is here today to share his thoughts on how to strengthen FL. So Vitaly, we're excited to have you. Please take it away.
All right. Thank you so much for having me and for taking the time to listen to what I have to say. The work I'm going to be talking about today was mostly done by Tao Yu and Eugene Bagdasaryan, and I will also mention a few results that are done in collaboration with other people listed on this slide. So all the credit goes to them. And if I say something outrageous, which I fully intend to do, that blame is on me. These fine people have nothing to do with the outrageous stuff I'm about to say. So, all right. So federated learning, I guess we're all in this meeting because I'm interested in it, because we believe that it's something that's going to be very useful and somehow is going to make the world a better place. But I'm going to start by asking a few questions that I feel people don't ask enough when they try to do research in this area. And I think these questions are very important because they can actually inform a lot of useful research. So the first question I'm going to ask is, why would anybody actually participate in federated learning? You got your data on your device or wherever. Somebody comes to you trying to convince you to join some federated learning setup. Why would you do this? So one question is that you're kind of a kind and altruistic person who wants to make a world a better place. That's fine. But in general, the world doesn't run on altruism. So there's got to be another reason why somebody might want to join federated learning. And I would argue, and maybe that's already explicit in the early work on federated learning, but I feel that this point is actually getting lost as the field evolves away from its origins. The key reason to participate in federated learning is that the model that you get out of federated learning is better than the model you can train yourself on your local data. So this is very important, because if you disagree with this point, it's likely that the rest of the talk is not going to make much sense. However, please bear with me and take this on faith, if you don't believe it right now, that the main reason why it's worth participating in federated learning is because you get a better model. If you don't get a better model out of federated learning than you can build yourself, by and large, most people just aren't going to participate. With this in mind, let me ask another question, which is, who are the people or users or devices that participate in federated learning? And if you go back to the early work on federated learning out of Google, and I understand many of the people who did this work are listening to me right now, so I hope I'm not misrepresenting anything you said at the time. But my impression is that federated learning is primarily designed for settings where different people don't have quite the same data. The data are non-ID across different users, heavily unbalanced. Some users have way more data. The most interesting applications of federated learning also seem to arise in settings where it's massively distributed. So you have millions of users, each with their phones. Also, phones are frequently offline, and so on. This is very important. And if that's motivation for federated learning, it seems like we should be doing research that takes these factors into account. And yet, as you'll see in a moment, a lot of research that's going on starts by ignoring these aspects of federated learning. It starts by assuming equal samples identically distributed and proceeds to derive all sorts of results from it, which I will argue are not going to be super useful for federated learning if it's actually going to be deployed in some kind of realistic setting. And another key motivation for federated learning is that people who participate in it care about their privacy. They want to get a better model that they can train on their own, but they also somehow want to train it in a way that doesn't reveal their own data. So vanilla federated learning, kind of federated learning 101, where in every iteration, the server takes a global model, distributes it to a bunch of participants. Participants go on to train on their local data and then share model updates. I would argue that this setting by itself is unlikely to provide much privacy. And the reason it's unlikely to provide much privacy is because if you look at these model updates and this information that participants in federated learning share with the server, it turns out that these updates actually leak a lot of information about users' data. That if you just look at what users contribute in this aggregation process, it's almost as revealing as the raw data itself. And the reason for that is very simple. It's because if you look at the gradients of model trained on local data sets, especially relatively small local data sets and relatively small batches, as might be the case in typical applications of federated learning, they leak information about the data. And they actually leak even more than users might realize. Of course, they could leak individual training data points. This is the standard issue of so-called membership inference, where you can test if a particular data point was included or not. But as recent research has shown, including some of the work that we have done in collaboration with Emiliana de Cristofari's group at UCL, it actually leaks information about various properties of the training data that actually have nothing to do with the learning objective. You're not just learning, it doesn't just reveal the things you learn for, it reveals all kinds of sensitive properties about the training data that you wouldn't even care about if you just looked at the learning objective. It reveals the presence of certain people in the data set. It can reveal, in the case of facial images, attributes such as gender and race. It could reveal in NLP models even who authored the text due to presence of certain telltale words in the text. We've even done some experiments where you can even do dynamic inference, where you can tell that at a certain period in time, some person appears in the training data set and then disappears from the training data set, even when the model is trained, even when the federated model is trained for something that has nothing to do with detecting presence of people or detecting individual identities. So there is a lot of leakage there. And of course, when you're listening to this, you could say, well, maybe there is leakage, but we have ways of dealing with this. Indeed, we do. For example, there is a beautiful solution called secure aggregation. This is a very clever cryptographic protocol. It uses some rocket science cryptography that I barely understand, but I'm willing to believe that it works, and it provably prevents the aggregator from inspecting what users are contributing into federated learning. So basically, it prevents any kind of analysis being done on model updates that are being aggregated. And that immediately introduces another problem, which is intimately related to the nature of the data on which you're training. Because if you're going to train on non-ID unbalanced users, which again, I reiterate, is the interesting, or maybe I shouldn't generalize, to me, it's the most interesting application of federated learning and the setting for which federated learning seems to be expressly designed. You have to deal with the fact that you're going to have, I'll call them, for lack of a better word, tail users. That is, users who don't look like the average users. And this issue with tail users in federated learning is going to create a whole lot of thorny privacy and robustness problems that I'm now going to spend 5 or 10 minutes talking about, because I feel that without dealing with this issue of tail users, it's unlikely that there's going to be progress towards having useful models for useful scenarios. So one issue that immediately arises with tail users, especially tail users in the presence of secure aggregation, is that you don't really know what they're contributing to the model. So they could contribute anything at all. And if some of them happen to be malicious, that is, they train in a way that doesn't follow the protocol that you ask them to follow, or they train on data that you don't expect, or that somehow is maliciously crafted, they can actually have direct influence on the model. And they can do various things to it, like introduce backdoors and do various model poisoning attacks. I'm not going to go into a whole lot of detail about this, even though I feel it is really an important issue. My apologies here. So that it's really an important issue. I will mention only a couple of things. So first of all, these attacks that could be done by tail users who submit something weird into the model, into the federated aggregation process, they're strictly more powerful than data poisoning. So there is a lot of literature on so-called data poisoning attacks against machine learning models. You can do much, much more in terms of influencing the model with model poisoning attacks in federated learning that you can do with just data poisoning. So that's one point I want to make. The second point I want to make about these attacks is that unlike conventional backdoor attacks, if you look at the backdoor literature, most of the attacks people do are just like weak adversarial examples. They do the same thing as adversarial examples do, only they require the model to be poisoned as well. Here you can do much better than adversarial examples. In particular, you can change the model behavior, or more precisely, a malicious participant in federated aggregation can change the model behavior without having inference time control over the input. So you can cause the model to behave differently on certain subclasses of its input space, and that actually doesn't require you, in contrast to conventional backdoors, to modify the input at inference time. So this is a different class of attacks that is just different from adversarial examples that enables malicious people to do other things. Okay, so there are problems. There are privacy problems and robustness problems in federated learning, but surely we have plenty of solutions for this. So one obvious solution, we're going to detect anomalies in when participants in federated learning submit something bad. Well, one problem with anomaly detection is that secure aggregation, this nice solution to privacy problems that I described, it provably prevents anomaly detection. But even if you could do anomaly detection somehow, you're back with the issue that you have non-ID participants that are all different, they're unbalanced, you have tail users, and you really have no way of telling the difference between a tail user doing something malicious or tail user just being a tail user, that is submitting something that doesn't look like the average. Another solution is so-called robust aggregation. And there has been a ton of literature on robust aggregation in the past few years, talking about how you can create models that are that cannot be influenced by outliers. And here, the very definition of the problem is a problem itself, because all that robust aggregation is going to do for you is effectively discard the or heavily suppress the contributions of tail users. Because the point of robust aggregation is to prevent tail users from influencing what the model is learning. And I'll show you in the moment that if you frame the problem like this, you're just not going to get a good model. And I'll explain what I mean by good. Basically, you're not going to get a model that tail users will be interested in using. There is yet another solution, differential privacy, which, as we all know, is the answer to every question these days. And I should say right ahead that some of my best friends are differential privacy people. Nevertheless, differential privacy kind of solves the privacy problem, and to some extent it solves the robustness problem. Most papers on differential privacy that I read end up with some kind of theorem. It never actually gets to the brass tacks of getting a useful model out of it, like suggesting a specific value of epsilon and what you get out of that value of epsilon. But that's fine, I guess. You know, we do need Fox and Stock papers, nothing wrong with that. However, differential privacy also loses accuracy. I mean, everybody knows that. but it loses accuracy, especially for tail users. So if you're trying to do federated learning in a setting where tail users matter, differential privacy, well, it's not going to lose accuracy everywhere the same way. It's going to lose accuracy on the tail. Because of that, it's also going to exacerbate unfairness. It's going to turn fair models into unfair models. If the model is unfair, it's going to become even more unfair, especially for tail users. And it turns out that privacy protections provided by differential privacy are also unevenly distributed, and they're much better for the middle of the distribution, and they're bad for tail users. So it's all very good, but it's not really like differential privacy in federated setting enables you to learn the middle of the distribution. But the whole point of the whole point of federated learning, I thought, is to try to capture all these weird users with weird stuff on their devices and help integrate their contributions into the model, as opposed to kind of learning the common part of the distribution, which admittedly can often be learned on public data. You don't really need federated learning to learn the middle. You might need it to learn the tail, but differential privacy doesn't do very well at helping you to learn the tail. Let me now come back to the question asked first. Why would a user participate in federated learning? I argue it's because the federated model should be better than models trained on local data. That's the primary incentive to participate. And here is the bad news. It turns out that a federated aggregation uses differential privacy or robust aggregation, even by themselves, let alone together. That is no longer true. You do not get a model that is actually good for individual participants. And by good, I mean better than local models. Here are some concrete numbers. So this is taken from a very vanilla word prediction task on a Reddit data set, which is kind of one of the standard benchmark tasks for federated learning. So you can see that with kind of vanilla aggregation based on averaging, for 9% of users, the federated model is worse than the model they can train locally. But if you use a very nice, robust aggregation mechanism, in this case, median aggregation, but it's actually similar for other aggregation mechanisms, for more than half of the users, the federated model ends up being worse than what they can train on their own. So why would they have even any incentive to participate if the federated model that comes back is worse than they can build on themselves? So to me, that's a strong disincentive, robust aggregation, to participate in federated learning. And you can see similar effects with differentially private aggregations. It's a little better for this task, but still there is a huge percentage of users who basically get no benefit of federated learning at that point. It seems like we have a trade-off. So this is going to be a conjecture. I'm not going to try to state a theorem here, but it's a conjecture that if you want to have accuracy, privacy, and robustness, it could be kind of standard, choose 2 out of 3. But my hunch is it's actually worse. That if you care about tail accuracy, that is, if you care about giving tail users an incentive to participate in federated learning and getting federated models that are accurate for these users, you actually only get 1 out of 3. That is, you cannot get tail accuracy either with privacy or with robustness. And the reason for that is kind of pretty fundamental, because to achieve privacy and or to achieve robustness, you have to suppress the contributions of weird users. But there's no difference between weird users and tail users. So here you kind of have a conundrum. So to have an accurate model, you need to incorporate contributions of the tail users. But for the model to be privacy preserving or robust against malicious users, you have to suppress their contributions. So it's not clear what you can do here. And my hunch is that there is really nothing you can do. You have to either lose their contributions, and then the model is going to be inaccurate, or you have incorporated, and then it's not going to be privacy preserving or robust. Unless you're willing to sacrifice something else. And now I argue that what you want to sacrifice is this idea that you're going to have one model to rule them all. There is no reason to have one model. That maybe the way to solve it is to take this central model, which by itself is not all that great. It's actually less accurate than models of that individual users can train on their own, and then proceed to adapt it to users' individual data. So now users can go ahead and do local adaptation of this federated model. And instead of a single model, you end up with lots of different models, maybe as many as one per user. But these models are actually going to be good. They're going to be accurate for the individual user, including tail users. So it turns out that now tail users, by participating in creating the federated model, and then taking that federated model and adapting it locally on their local data, they end up with a model that is better than the federated model and better than the local model they started with. So potentially it's the best of both worlds, but it comes at the cost of having individual adapted models instead of having a central federated model. And now participants actually do have incentive to participate because they do get better models out of this than they can get on their own. And we actually explored a whole bunch of different adaptation techniques. Fortunately, there are plenty in the machine learning literature, including approaches such as fine-tuning, basically directly adapting the global model, and using more advanced techniques like multitask learning of federated model and local task and knowledge distillation and so on. And it's kind of interesting how different techniques work differently in different settings. And it's not like there is one technique that dominates all others. But the good news is by using various combinations of these techniques, you do end up with locally adapted models that are significantly more accurate for most individual users than federated model. They actually give a concrete incentive for individual users to participate because, like I said, even though the federated model itself is not good enough, by using one of these adaptation techniques, and again, it's different techniques for different tasks, but by judiciously choosing the right adaptation technique and adapting the model locally, you actually end up with something that is quite good. So that, I feel, is the solution to the conundrum that I presented. That's how you preserve privacy and robustness in federated learning, by creating maybe a poor quality federated model that's privacy preserving and robust, however, is not sufficiently accurate, and then distributing it to local users and letting local users create their own individual models that actually end up being good. And another important point that I want to make is that this improvement in accuracy is especially good for tail users, which should not be all that surprising because, as I keep saying, at the core of all existing privacy and robustness techniques that I know is suppressing the influence of tail users. So it's no wonder that centrally trained federated models end up being inaccurate for these users. And local adaptation gives tail users a way to put their contribution back into the model where it has been lost, and therefore they really benefit a lot from this. And also the good news is that it's better than their local model, so there is still an incentive. So it's still better than what they can train on their own. So they do benefit from participating in the process, and they do benefit from other people's models. And of course, you can read the paper for more details about how we do adaptation techniques and which one works better where. So what are the main takeaways from the story that I try to tell you today? So first one is that it seems that to achieve privacy and robustness against model poisoning attacks, you have to bound the influence of outliers when you do aggregation. That seems inevitable, and a direct consequence of this is that you end up with models that are not accurate for tail participants. And when I mean tail, by the way, here, I should have said this earlier, but I want to make this very explicit. I don't mean just one individual user. There could be whole categories of users for whom this effect manifests. For example, we did experiments with natural language models that turned out to be highly inaccurate for users who communicate using African American vernacular, which is kind of a dialect of English. So now you have entire category of users, in this case actually a sensitive category closely correlated with race, speakers of African American vernacular, for whom the model ends up being especially inaccurate because their contributions are suppressed by the privacy mechanism or robust aggregation mechanism. So, so this loss of accuracy on tail users is actually a pretty big deal if you want to have a high quality model and a fair model. So that's the first point I'm trying to make. The second point is, it's not a point, it's a conjecture that there is no way to balance this in a single federated model, that no matter how you try, something gotta give, that you will lose one, or I actually suspect both of privacy and robustness if you try to get tail accuracy. That is, I will find a way to attack your model if you allow contributions from tail participants to influence the model significantly. But I feel there is hope in having, instead of a single model, having lots of models. We experimented with models for individual participants, but it could also be done for certain categories of participants. You can even think of a protocol that would identify participants that have something in common and adapt a model for an entire subclass of participants as opposed to an individual participants. There are lots of techniques coming from ML literature that seem to work pretty well and produce good quality models. So if you're willing to give up on the dream of a single federated model that's privacy preserving, robust, and accurate for everybody, there is really a lot you can do, and I feel like this actually does give a lot of hope to federated learning as a technology to produce really useful model for lots of people, including people who don't seem to benefit from it right now and don't seem to have any incentive to participate. So that's pretty much what I had to say today. For everything I talked about today, there are a few papers on archive that you're welcome to look for and read. And I'll be happy to answer questions, which I understand are submitted via some system called Dory, but I was told that somebody will tell me what the questions are. So.
That's right. I'll take charge of that. Thank you so much, Vitaly, for this exciting talk. And I already see a couple of questions posted here. While I'm working on actually pulling up the questions on the screen, the first question from Emiliano is, how generalizable is the local adaptation approach? Will it work on all kinds of data sets? Interpreting that a little bit, what if you have, say, very sparse data sets, for example, where some users only have a single example on locally, or
right?
What
So it's very that's a very reasonable question to ask, and it's of course a little hard for me to say. If there is no local data, of course, local adaptation is not going to help. Local adaptation as a technique, it presumes some availability of some local data set, and it works the best when that local data set is sufficiently different from the middle of the distribution, from what the central model has learned. However, I would argue that even with this limitation, it's still a very useful thing. The reason being that people, like, if you're running some kind of federated learning setup, the people you really want to incentivize to participate are people who have data, and that data is not like your data, and it's not like publicly available data. You really want somebody with kind of weird, like off-key little data set that has different properties, maybe different subclasses represented more or less. You want to incentivize those people to participate in federated learning. And these are exactly the people who do not benefit from it right now. And these are, to answer your question, the types of people who are going to benefit from local adaptation because they have enough local data to actually adapt the model properly, and their data is sufficiently different that local adaptation is going to give them higher accuracy than the federated model.
Thank you. The next question is from Gary Yoshi. Thanks for an awesome talk. For tail users, local adaptation of a global model may not necessarily work well, especially if the global model is biased towards the typical users. Do you have any ideas on how to further improve model adaptation for tail users?
Okay. I mean, this is a fair point, and obviously these are kind of the incipient stages of this research. So in the paper, when we wrote it, we tried a whole bunch of techniques that we feel are going to work better for certain categories of users than others. So far, we haven't been able to convince anyone, to be honest, that local adaptation is useful. So we will try to work on the problem of how to make it better once we convince people that the basic approach works, which is admittedly still a work in progress.
That's good. Next question is from Dan Ramage. Nice overview of the tension in modeling heads versus tails. These matter from bringing FL to actual real products. To what extent do you see the tail user issue overlooked by the rest of the centralized ML community too? For example, optimizing overall, per example, loss accuracy, etc.
Sorry, I missed part of the question. To what extent is what overlooked?
To what extent do you see the tail user issue overlooked?
Right. To what extent tail? Okay. So this question is very difficult for me to answer, is because I'm not part of the ML community. I am a security and privacy person. I've never had good luck, any luck at all, communicating with ML community and so on. So to what extent do they care about tail users? I don't think they care about tail users per se, but they want accurate models. And I would argue that for the settings where federated learning is being promoted for, like predictive models on phones or personalized medicine or all these good applications, for those applications, you have, well, empirical accuracy for individual users is going to matter. Otherwise, nobody is going to use your system. And if nobody is going to use your system, you have to care about tail accuracy, because otherwise your system is going to be useful, not very useful for users. So I don't know to what extent ML community cares, but my sense is that users who are going to allegedly use these federated models for various tasks, they care if the system is useful or not, and to be useful, it needs to take tail accuracy into account. That's my answer.
Makes sense. And perhaps interpreting that question just a little more, and do you see some of these tail user issues also arising when you apply differential privacy to models on the server, or are these specific to federated learning?
I'm sorry, I really don't know how to answer that question, right? So to what extent?
That's totally fair.
Yeah, I don't actually know if anybody's using, for example, differential privacy or robustness for real systems based on federated learning. They will encounter these issues prominently, I feel, if these models, if these approaches actually start getting deployed.
Great, thank you. Next question is, given this notion that there is no guarantee that a federated model performs well on user data, how do we incentivize people to participate? Does this necessitate ideas involving data as a commodity for which users should be financially compensated?
Okay, so that's a great question. And of course, there are other ways of convincing users to contribute their data. Like if you give them a financial incentive, they might be willing to sell their data because they don't care. But in that case, it's not entirely clear to me you need federated learning. You can just pay people for their data, collect it all in like Mountain View or Cupertino or wherever, Seattle, train on it, and life is good. I feel, and maybe I'm wrong, and there are certainly plenty of people on this call who know much better than me, that one of the reasons federated learning came about, and one of the reasons why companies like Google are so excited about it, is because it's a way of telling people, like, your privacy is not going to be affected. Your data is never going to leave your phone. And if that's how you convince people to participate, I don't know how to combine that with paying them. Or maybe you're talking about like both, like if data never leaves and we pay you for contributing your data, but then what are you getting? Like if you're training a central model that suppresses influence of outliers, why are you paying outliers to contribute their data if you're going to ignore it anyway? You can probably do just as well training on public data. So if you want an accurate model, you somehow want tail accuracy. So I don't feel like how paying people for data is actually going to address the key tension inside federated learning here.
Thank you. And apologies, I reloaded the dory and the order of the questions changed a little bit. So apologies if you slipped down, but I'll try to get through as many as we can here. And Vitaly, I think you should be able to see them on your screen as well.
I'm trying to, and unfortunately it's not. It's just spinning like a blue circle on my screen and not showing me Dory questions. So unfortunately, I gotta rely on you. Yeah, I've been kind of clicking here.
Apologies, happy to read them for you.
Yeah.
Next question is from Thanks. Thanks for a great talk. How much extra local computation is considered a worthy trade-off for enabling benefits of personalization?
No, that is a good question. That's a great question. So we measure it, but we probably not measure it enough. So it's a little bit of local computation, equivalent to a couple of rounds of training, but arguably it's a little more. I mean, it's not a little. It's actually like more, much more. Well, not much. Sorry. It's more than you have to do just to participate in federated learning. Yes, so there is a price to pay. And that's a meaningful price because you need to do local computation. So you can think of a scenario, if you're talking about like IoT devices or something like this, that can only do very little local computation, in which case local adaptation has a cost for them, which might be too much because you waste energy and so on. And that needs to be measured better. I mean, we do have some measurements in the paper, but we could probably do more analysis on how much local adaptation you can do. But for a lot of these techniques, it's on the order of a few rounds of training on the local data set, treating federated model as a pre-trained model.
Makes sense. And he's also writing, if we only train a global model, we only need part of the clients to participate in a few rounds. But presumably, if you personalize, you would need an additional computation on all clients.
Yes, but not in every round. They can do adaptation after the federated model has converged. So there doesn't seem to be any other way. So if you want tail users, you want their contributions to enter the model, you only have two options, it feels like, unless I'm missing something fundamental here. Either you let them go into the federated model, in which case you're going to have privacy and robustness issues, or you have to have them train locally at least once. So every tail participant whose contributions you want reflected in the model will have to do some training. So I don't see any way around it, other than sort of clustering them somehow, like, you know, speakers of a certain dialect, users that have more images of a certain subclass. In that case, you can sample from them, and we kind of had these ideas, but admittedly, we've never actually explored how to do this sampling in a meaningful way.
Sounds good. Next question is from Dimitris. Thank you for a great talk. Would a hybrid version of FL and local adaptation lead to further improvements? For example, find a set of users.
I believe that's the way. I believe that some kind of hybrid version is going to be the best. I think we haven't explored it ourselves because we've been, you know, just trying to push individual adaptation. But some kind of hybrid version seems to be seems to be the right way to go from here. Yes.
Great. Next from Adam Smith. What happens to tail users who don't, on their own, have enough data to even figure out if the global model is good for them?
Well, I would argue if they don't have enough local data, then global model is good for them, because if they don't have enough, like this is an empirical fact. You can train a model on your local data and then compare its empirical accuracy with empirical accuracy of the global model on the same test data set, right? So if you don't have enough local data to train local model, yeah, I mean, you got to participate, because that's your only hope of getting a useful model out of anything. But maybe the question is, why would you even contribute more? Like, you could maybe free ride. You could get you could just use the federated model. But if the price of getting the federated model is participating, you have to pay that price, because you're not going to train anything locally that's useful, unless I'm misunderstanding Adam's question.
Makes sense to me. Next from David Evans. It's hard enough to test a single model for accuracy, fairness, non-toxicity, etc. Once we move to a setting where individuals, groups have their own personalized models, do you have any ideas how we would test those models for these necessary properties?
Again, maybe I'm missing something very important here, but you would test them in the same way as you're testing federated model. Because I would think that if I am the only user of the model, the only thing that matters to me is if the model is accurate for me. I don't even know, like, the fairness issue, again, unless I'm missing something, it doesn't seem to arise all that much here, because I would say that I'm the only user of the model. I'm not going to apply to anybody by myself. It's like, think of keyboard prediction. I wanted to predict what I'm about to type. I don't care if it's accurate for you or somebody else. I don't care if it's fair. I just want it to be good for me. So you test it in exactly the same way, but there are many few properties that you care about. I would say maybe the only thing you care is if it does a good job for me. Although I can see now that I said it about fairness, I can see there are fairness issues that could arise in that case. I could actually, sorry, let me take that back. I said something rashly, and now I totally see a fairness issue, because, okay, ignore that part of it. You would test it in the same way as you would test the federated model.
And I think we have time to take one more question from Benes Mehdi. Fantastic talk. You alluded to knowledge distillation as one technique to tame the tail. Can you provide an introduction for that? We've shown federated distillation is more sensitive to non-IID compared to FL.
To be honest, I mean, we're not using federated distillation. We're just using distillation locally. We're just trying to distill knowledge from federated model to better adapt the local model. So this is a somewhat weird use of knowledge distillation. All I can say, and Eugene, who I believe is on this talk, might be able to provide a better answer offline, but empirically, we feel that somehow it just gives better results than other techniques. For certain kinds of data sets, it seems to do a better job combining local data with a federated model by doing distillation on the federated model to local data. Other than that empirical result, off the top of my head, I unfortunately do not have a great explanation for why that is, but Eugene might.
Thank you, Vitaly. Thanks for sharing your thoughts. There's a number of additional questions in the Q&A tool here, the Dory.
Yeah, I'd love to engage with them somehow, but for the life of me, I can't get into it. So I don't know what you guys want to do. I'm happy to.
We'll try to work with you or find some way to get the.
Yeah, just go into chat with me or something. And thanks a lot for listening to me. I appreciate your time.